This is the second video on the topic of graphs of rational functions. Here specifically going to start off with the square of the reciprocal function, or I guess you could call it the reciprocal of the squaring function just as well. Y equals 1 over x squared, or f of x equals 1 over x squared. And you can write it in exponent notation also with a -2 exponent. There's some similarity to the y equals 1 over x function that I started the last video with, the reciprocal function. Because, well, if you take 1 over a number, you get a smaller number for the most part, as long as x is bigger than 1. And if you're going to square it, you're going to get a similar sort of thing. If you square a number bigger than 1, the square will be bigger than 1, and we'll have 1 divided by a number bigger than 1, which will be smaller than 1. So as with the reciprocal function, as you move to the right, this thing goes down towards the x-axis. It gets smaller and smaller. As x approaches infinity, y approaches 0. Now with the reciprocal function, if we had y equals 1 over x, if x is negative, then we would have 1 divided by negative, which gave us an odd function where we had a branch of a hyperbola over here, and then we had another branch of the hyperbola here in quadrant 3, as you may recall. We don't have that here. This is actually an even function. In exponential form, it's x to the power of -2. Any power function like that, where you have x raised to an even number, even if it's a negative even number, will give you an even function. And so this has even symmetry as compared to the y equals x to the -1st, which had, or 1 over x, which had odd symmetry. So if you're to fold the graph at the y-axis, the two sides of the graph would coincide. You should try to familiarize yourself with this basic function, just like with the reciprocal function. Another difference is this one's a bit steeper. So with the reciprocal function, as you head towards 0, that means the x values are getting smaller and smaller. So for example, x could be 1/1,000,000. Well, the reciprocal of 1/1,000,000 is 1,000,000. So for really small values of x, you would have really large values of y for 1 over x. That's amplified here because of the squaring. So if you had 1/1,000,000th, that's 10 to the -6th. Well, the square of that would be 10 to the -12th. And so its reciprocal would be 1 over 10 to the 12th, which is what, 1 trillion, I believe. So it's actually steeper heading up towards the asymptote here we have in the middle. So as with the y equals 1 over x, the horizontal asymptote is the x-axis. The vertical asymptote is the y-axis. That's the same as it was with y equals 1 over x, the reciprocal function. But there is the difference that the x and y, the y values anyway, on the left branch of this graph are in positive territory, whereas they were down here in the third quadrant for the reciprocal function. So if you don't remember the reciprocal function, look at this graph, look at that graph, compare the two. Now we can shift this in the same sort of way. I decided I'd do a few things to it here. So here, for example, we can have g of x equals the opposite of 0.5 over the square of x plus 4. So if you're comparing that to this function here, we still have something squared. Here the x is squared. Well, if you were to replace x with x plus 4, that's going to have the effect of taking the graph we see here and shifting it 4 units to the left. Remember, the x plus 4 shifts it in the sort of backwards direction as far as x is concerned. I don't have a Y shift here, but I do have a negative, which is going to reflect this with respect to the x-axis. So that's going to reflect Y, so to speak. If this is our original Y, well, our new Y is going to be reflected. And the 0.5 also has an effect on it. It amounts to a vertical shrink, shrinking it in the Y coordinate. Though the original graph goes to infinity, so what happens when you shrink infinity? So it's a bit subjective. Well, based on just knowing what the y equals 1 over x squared looks like, and the fact that this is a transformation of that, could actually do a quick sketch of it, or could try to. Let's see what we can do here. So if we had, if that's our x-axis, and this is our y-axis, and we're going to shift that 4 units to the left. Asymptotes should normally be broken lines, and then the graph itself will look roughly like this. It's going to be symmetric with respect to that asymptote. You have some sort of a rainbow color going on here. So just a real rough sketch here. We'll look at the official graph on GeoGebra. But just knowing it turns it upside down and shifts it to the left 4 units makes it pretty easy for me to come up with a rough graph of our function without actually calculating any points whatsoever. Though for the more refined graph, if you're doing this for homework or quizzes or tests or something, you should actually calculate a few points. One point to notice is that I can't plug in -4 here, because if I did, I'd have -4 plus 4, which is 0, and the square of that's still 0, and we can't divide by 0, which is what that asymptote, that vertical asymptote, is all about. Just to look at GeoGebra for a moment here, so I'll have to change to a new share for that. You can see the red curve here with the asymptote in the middle at -4, y equals -4. As I said, compare that to the original graph, so they both have the same horizontal asymptote, which is the x-axis, meaning that as x grows in absolute value, either going off to the left or going off to the right, the overall value tends towards 0, which is what the x-axis has. The y value is 0. That's true for the green curve, also true for the red curve, which, as you see, is reflected upside down relative to the green curve, and the asymptote moved, as I mentioned a couple of times here. You might also see some of the effect of the 0.5 multiplier. What that does is it shrinks this, sort of pushes it down, compresses it in the vertical direction. It's hard to see that really, but they don't look that different. But one way you might make the comparison is if you look back here between -1 and 1 on the green curve, you'll notice the y values were 1 in both cases, so the space between these is 2. If you look at the comparable things here, which would be from, say, well, actually, let's look at it this way. You go up here 1 unit to get to 1. If you go down to -1, which is also 1 unit, you can see the spacing here is smaller than it was up here. Here the spacing was 2. Here it's a bit more like maybe 1.5. And that would be comparable to what something you're seeing up here a little bit higher. So that's why you can think of it really as if the green curve is sort of smashed down, compressed downward. And of course, after that, it's it's reflected about the x-axis, or maybe before that's reflected about the x-axis. But either way, it ends up compressing the picture. Now I want to say a little bit more about the horizontal asymptote, which is the x-axis. The line y equals 0 is the x-axis. Now the reason this tends towards 0 in terms of the end behavior, that's because if you look at either of these graphs, the green one or the red one, look at the curves that we start with. So if we were to zoom in, close, you can actually see the red curve is approaching fast, the x-axis faster than the green curve is here. That's going to continue throughout. Zoom back out here, get more like the, more centered on. Okay, let me go back to our previous screen here. And let's see, there we go. So I saw the graph. It's kind of like, of course, much better graph than what I drew here, but get the rough idea. Oh, so what I was saying here is in both of these cases, notice the numerator is constant, whereas the denominator is a variable, so it can change. Well, if you have 1 divided by a number, it's going to tend towards 0 as that number gets bigger and bigger. And similar sort of thing happens here. You can actually generalize that statement to say that whenever the degree of the denominator is bigger than the degree of the numerator, we're going to have similar behavior, so that the overall value of the function, which is the y value, is going to tend towards 0. So you're going to have y equals 0 as a horizontal asymptote. So the x-axis is always a horizontal asymptote if the denominator has a higher degree than the numerator. In this case, the degree of the numerator is 0, the degree of the denominator is 2, which is definitely higher than 0. But even if it's only 1 bigger, that still means that eventually you're going to have the y values tending towards 0, which is, again, the x-axis. Okay, let's look at a case where that's not going on. Look at a situation where we have quite a bit going on, really. So here I have a function f of x equals, again, this is a rational function. The numerator and denominators are both quadratic polynomials, and that's the definition of. Well, in this case, the degrees are the same. So we're going to have a different sort of horizontal asymptote. We will have the horizontal asymptote as long as the degrees are the same. And we actually saw how to find that horizontal asymptote in the last video where we had the numerator and denominator with the same degree, except they were linear in that case. It turns out that for a large enough value of x in terms of its absolute value, which means you're going to the right or going to the left, either way, the 8x squared and the 4x squared will dominate the numerator and denominator in the same sort of way that determine the end behavior for polynomials. And so for a large enough value of x, it turns out that the 10x here doesn't matter. -3, -1 don't matter. If x is 1,000,000, 10 times 1,000,000 is a pretty good sized number, but it's much smaller than 8 times 1,000,000 squared. So the squaring here means that that term will dominate the numerator. So for a large enough value of x, almost everything, relatively speaking, proportionally, almost everything in the numerator comes from the 8x squared term, and similarly in the denominator. So it turns out we can actually just compare the lead coefficients here, 8 and 4, to figure out what the horizontal asymptote is. It'll be the line given by y equals 8/4. So I have that down here someplace. Yeah. If they have the same, if there's the same degree in the numerator and denominator, then we can apply this technique. Take the lead coefficient of the numerator, divide it by the lead coefficient of the denominator. And of course, 8 divided by 4 is 2. So that's going to be a horizontal asymptote. the vertical asymptotes, and really most of the rest of the interesting information we're going to get by looking at the idea of letting something be zero. There's actually three things that could be zero. X could be zero, Y could be zero. The denominator could be zero. It actually can't be zero, but if we set it to zero, that gives us information. And the numerator could be zero, but it turns out the numerator being zero and Y being zero are really the same situation. So at least in this case, and usually. The vertical asymptotes you get by setting the denominator to zero. If the denominator is zero, then we're dividing by zero, which is impossible. So the vertical asymptotes are actually going to break up the graph. And the graph cannot cross the vertical asymptotes. So you set the denominator to zero. The denominator was 4x squared minus 1. We can factor that. That's what I did here. 2x minus 1 times 2x plus 1, right? Difference of squares. If you set 2x minus 1 to 0, then 2x equals 1. Divide by 2, you get 1/2. And similarly, you can get negative 1/2. So we have 2x values that will cause the denominator to be 0. And each of those is a vertical line. X equals negative 1/2, x equals positive 1/2 are the two vertical asymptotes. They're nicely symmetric, which suggests that, well, maybe there's some symmetry going on here. And I don't know about that. Let me see the denominator. It's certainly a symmetric function. It's an even function. Numerator isn't though, so I don't think we're going to quite have symmetry going on here. Could check whether the function is even or odd by plugging in try f of 1 and f of negative 1 and see what happens there. You'll see that those are not the same values, so it's not an even function. They're also not opposite of one another, so it's not an odd function. So it's neither even nor odd. I'll leave you to do those calculations. So once we look at the graph, it'll be clear that that's the case. Okay, so you set the denominator to 0 to find the vertical asymptotes. We're also going to usually want to find the y-intercept. That's pretty straightforward to find. You just plug in x equals 0. F of 0 is 3. Simplifies as negative 3 over negative 1, which is 3. So the y-intercept is 0, 3. The x-intercepts, of course, you find those by setting y to 0. So we have that here. Now, if you're solving the equation 8x squared plus 10x minus 3 over 4x squared minus 1 equals 0, so if you have a fraction equals 0, you can actually multiply both sides of the equation by 4x squared minus 1, provided it's not 0. If it's possible that it can be 0, then we've got to be careful about that. But we've already really dealt with the situation of letting the denominator be 0. We know what values would make that happen. So as long as we don't end up with one of those values, we're fine. That'll be a topic for maybe another video. Though it's often a topic I kind of ignore in college algebra and figure people can worry about it later on. Anyway, we can multiply both sides by 4x squared minus 1, and we have an equivalent equation. 0 times 4x squared minus 1 is still just 0, and it would cancel out the denominator, so we get this. It actually turns out in general that the only way a fraction can be 0 is if the numerator is 0. That's not really enough information because you have to make sure the denominator doesn't become 0 at the same time, but if there's anything that's going to make the thing 0, it's going to have to be the numerator that being 0 that does that. Quadratic, so you could use the quadratic formula. I just factored again. You see 12, I think that factored correctly. So if you set 2x plus 3 to 0, then you would have 2x equals negative 3. If 2x equals negative 3, then x equals negative 3/2. I wrote it as negative 1.5, same thing. Or you could have 4x minus 1 equals 0. If 4x minus 1 equals 0, then 4x equals 1. If 4x equals 1, then x equals 1/4. I wrote it as 0.25. So those are our two x-intercepts here. Okay, so that's really all the information. So if you're graphing this by hand, and that's something you should practice, preferably with graphing paper, and if you're plan is to go into the sciences or engineering, or heaven forbid, become a mathematician or something like that, you really want to develop those graphing skills where you can create a nice curve on graphing paper. But it's also good to be able to use the technology, and that's what I'll use here. Since I'm doing this on a computer, I really would have to use some sort of technology, at least the computer, though I could certainly put some graph paper up here on the screen and do it by hand. Maybe you should try something like that, but I'm not going to. I'm just going to go to GeoGebra and work with that. Okay, so we'll have to remember this function here as we go into GeoGebra. So I went to GeoGebra, but it did not bring you with me. I need to change the screen share. Okay, so now you should be seeing this. I'm going to go ahead and turn off the other graphs. And then down here in the input box, we're going to put what we need. So what we have here is f of x or y. I don't think the computer necessarily cares, or the program, if I call it f, but I'm kind of in the habit of calling it y, so I'll do that. So y equals, and I want to use parentheses around the whole numerator, whole denominator. So the numerator 8x squared, 8x, just the second power, plus 10x, what was it, minus 3. Close the parentheses, and you're seeing a parabola at this point. And then I'm going to take that and divide it by, again, parentheses, what was it, 4x squared minus 1. So 4x squared minus 1, close the parentheses, and there we get our picture. Now, if you look at the picture so far, can't really tell for sure that this isn't, well, it couldn't really be a polynomial function. Polynomials are continuous, and what I'm looking at here, it's not obvious to me just yet that this isn't a continuous graph. But if it were continuous, it wouldn't be a function, because it would seem to, well, actually, I don't know for sure. It looks like it might fail the, no, actually, as a function, it can't fail the vertical line test, period. So, yeah, it could be a polynomial, maybe, except I don't know how it would get, yeah, it would have to go backwards on itself here, kind of to get there. So it can't be a polynomial, not if it's a function, and it definitely is a function. Well, if we zoom out a bit, we might start to develop a sense, but still can't really see. But notice it seems to be almost symmetric. I mean, we've got a branch over here and a branch over there that kind of like the reciprocal function seem to be mirror images of one another. However, this middle part is not really symmetric in an even sense. It's really more symmetric in an odd sense. So well, actually this was odd also. So that's odd, and this is odd. But if you were to rotate this actually 180 degrees, it's close. But I think it's kind of elevated up here, so it does. The asymptote is, horizontal asymptote is not the y-axis, so that's kind of what prevents it from being a true odd function. Right, it's not odd because f of 1 would be 18 minus 3 over 3, so that's if x is 1, I think I got minus 15 over 3, so 5. Whereas if you plug in negative 1, this would be 8 minus 30 minus 3, and this would still be 3 down here, so definitely not the opposite of what was it, 5? Anyway, I'm very confident that it's not an odd function, but I've been very confident, been wrong before, so, but it doesn't quite look like it, though it does look kind of close. Okay, so anyway, back to talk about some of the details we had before. So you may recall that we had two different vertical asymptotes and can see them here. You can see them better if we zoom in. One of them was at -1/2. So if we zoom into -1, +1 here, -1/2, yeah, looks close. Certainly can't tell for sure just looking at the graph here. It's one way in which the algebra is a little bit stronger than the geometry. However, the geometry does give us a nice visual presentation, which is not as abstract as the algebra is. Now, if you think about it, it was symmetric with respect to the asymptotes, so they were symmetrically placed either side of the y-axis. One was at 1/2, the other one was at -1/2. And you can see that in this area, at least, this middle piece is closer to this than it is to that, I think, down in the corresponding spot. Here we have, so if this were an odd function, it would have to actually pass through 0, 0 here, which it does not. So it might actually be a transformation of an odd function. I'll leave you to think about that as to whether this might be a transformation of a function which does pass through 0, 0, but, which then might be odd. So we have to move it down 3 units to get there. So I'm not sure that these two branches would be symmetric with respect to the x-axis in the way they have to be. Anyway, we need to quit dwelling on that and get back to the point at hand here. Okay, so we can see the y-intercept of 3. You'll recall we had two different x-intercepts. One of them was 1/4, which is right here. The other one was -3.5, which is here. We got y = 2 was the horizontal asymptote. The asymptotes don't show up here in the program. They're not part of the graph anyway, so they really shouldn't show up unless they're going to be a dashed line or something to indicate them. And there are actually 3 branches to this, and they don't connect. The graph cannot cross. It gets across, but it does not actually touch. It doesn't cross in the sense of touching the lines x = 1/2 or x = -1/2. And so I know algebraically that it breaks it up into 3 pieces. Though zooming back out here, it doesn't make it, you can never zoom far enough out here to see as an absolute fact that the graph is broken. Because essentially it goes up to infinity and sort of jumps across some magically the x = 1/2 line, and then it becomes this part in the middle that's between -1/2 and +1. Kind of a neat thing. So if you zoom out far enough, it really just looks like the reciprocal function that we saw before. It looks like a cross from a distance. Okay, that's a lot of information here, so I'll leave you to maybe explore that function on your own and see if you can replicate the work I did or do similar functions even better and write something of the same type. I'm sure they have stuff in the homework that's similar to this where you have a quadratic divided by a quadratic. Might be a little bit easier in some cases. But this one's pretty easy. I don't know that the topic itself is not necessarily all that easy, but as these things go, this is about as easy as this type of thing is going to get. Okay, so anyway, we'll leave it at that. And again, thanks for watching.